Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSE in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the coloring graphs. So you already know that what should be the graph here. So graph is nothing but a set of vertices and edges, which is going to have vertex set and edge set. So where the graph sets, we're going to have a set of vertices. So the vertex and all will be treated as a vertex set here, and then the edges are going to be represented as edge set here. So the graph is nothing but a collection of vertices and then edges. And so the vertices are going to be adjacent here. So whenever there is an edge connecting between the two vertices, so the edge is a vertex is nothing but a adjacent to another vertex. So when I'm going to say that is, so whenever an edge is going to be connecting between the two vertices, then that can able to called as a the vertices are going to be adjacent. Similarly, the edge is going to be incident to its endpoints. And the next one is the degree. So what is the degree of the vertex? How we're going to find it out? So the degree of the vertex is nothing but number of edges that are going to be incident on it is nothing but the degree of the vertex. So the degree of the vertex is going to be denoted as degree of V. So where the number of vertices that are going to be incident on this edge is nothing but degree of the vertex. In case of undirected, so the how many vertices that are going to be incident on this edge vertex, so that and all will be treated as an degree of the vertex. So degree also means the number of vertices as well. So suppose if I'm going to have a graph like this, so A, B, C and D. So what is the in degree of vertex here? So in degree is number of vertices that are going to be incident on A, number of edges that are going to be incident on A is 3. So in degree is 3. Similarly for C, 3, it should be also 3. So in similar fashion, what I'm going to say is, so if I'm going to have directed edges like this, so the in degree will be treated as 3. So in this case, it should be 2 only. And similarly, the number of edges, or degree means the number of edges that are leaving from vertex A, that should be treated as out degree, that should be 1. So the degree of the vertex should be in degree plus. So the degree of vertex should be calculated as in degree plus out degree. So that should be 2 plus 1, that should be, so the degree of A. So like this we are going to be calculate the degree of the vertex. And the next one is paths and cycles. So paths and cycles is nothing but, so the path is nothing but a sequence of vertices. So that should be represented as V0, V1, V2 and Vn. So where there is an edge connecting Vi and Vi plus 1 for I equal to 0, 1 to n minus 1. So the path with the same ending, starting and ending vertex or ending point, what we called as a cycle. So a graph is simple if there is no edge is going to be repeated. Otherwise, a cyclic graph has no cycles. So the path is nothing but a sequence of vertices, and there is going to be connected by an edge Vi and Vi plus 1. So the path is nothing but the so whenever there is a path, so whose starting and end point is same, so that one is able to call it as a cycle here. So if I'm going to have a graph like this, so what is the path that is going to be connected from A to E? So I want to find it out. So for that I'm going to have this the path. So AB, BC, CD, D. So this is the path 1. Otherwise I can able to go directly. So path 2. So A to E, and similarly I can able to go for A to D, D to E, and similarly I can also go for A to B, B to C, C to. So these and all will be the paths here. So the path is nothing but the sequence of vertices. Whenever there is an edge that is going to be connected between the vertices. So whenever the starting vertex and ending vertex is also same, then I can able to call it as a cyclic. A to B, B to C, C to D, and E to E. So here A to B, B to C, C to D, D to E, and E to. So this is nothing but a path here. So it is going to contain the closed cycle. So we should be able to call it as a circuit as well. So then I can able to, that should be the cycle. And next one is that adjacency matrix. So normally we are going to be use this adjacency matrix, so that is going to be represent the vertices and the edges of the graph. Normally, this adjacency matrix is going to be represented in the form of n by n. So there the entry should be 0 or 1. So ai equal to 0 if there is no edge from vi to vj, otherwise it should be 1. So the adjacency matrix of the simple graph with n vertices is binary of size n by n, such that each entry of j is either 0 or 1. So if I is 0, then there is no edges from vi to vj, otherwise it should be 1. So let us consider a graph. So how are we going to represent the adjacency matrix here? So we have to consider the set of vertices along this rows and then columns. And whenever there is an edge between them, so A and B, that should be represent 1. So remaining all should be 0. So also 1. So similarly for B, it should be BA and BC. So it should be 0, remaining all 0, and there should be 1 for C, CB and CD. And for D, D2A, and then D2C. So like this we are going to represent it. So whenever there is an edge between the two vertices, then one should be represented as 1. If there is no edge, then I can able to represent it as 0. So what is coloring here? So the graph coloring is nothing but the assignment of colors to the vertices of the graph. So if I'm going to talk strictly, so the coloring is nothing but the purple coloring if no two adjacent vertices is going to have the same color. So the graph coloring is nothing but the assignment of colors to the vertices of the graph. So whenever the graph is going to make the coloring such that no two adjacent vertices should have the same color here. So let us consider this graph here. So if I'm going to take the first one as red, so similarly I can able to mark the next color as red, means then two vertices are going to be coincide. That's why I'm not doing that. So I am going to make the another color here. If this color is done, so if I'm going to make it as another color red here, so that no two adjacent vertices are going to coincide. So if I'm going to consider this as the third one, so I'm going to take this as the under vertex, and so I'm going to go for the blue color here, and this should be yellow, and this should be red. So similarly, if I go for red, means then these two will be coincide. That's why blue also it is not going to be matched, and yellow it is also not going to match, and red is also not going to be matched, since all the nodes are going to be coincide here. So that's what I'm going to go for an orange here. So like this, we're going to be color the graph such that the no two adjacent vertices are going to be coincide with each other. So let us consider another graph. So let us consider this graph. So if I'm going to make it as one color here, that should be red in this case. So then what should be the adjacent color? So this is under color. So I can able to write it as blue. So that no two vertices are going to go inside. And here, if I'm going to consider this, I'm going to write it as green. Okay. Then if I'm going to write red, it is not possible. Blue is possible since that no two colors are going to go inside. So I'm going to apply blue in this case, and if I'm going to apply red in this case, no two colors are going inside, no two vertices are going to be go inside. And if I'm going to apply red and blue, and if I'm going to apply green, also going to go inside. So that's why I'm going to apply brown. In this case, so this is the way of coloring the vertices. So here I'm going to make it as a full color, that should be red in this case, and this should be the blue, and this should be the green, and this should be the brown. So the chromatic number of this graph should be 4. Next one, coloring planar graphs. So a graph is said to be planar if it is going to be drawn in a plane without edge crossing. So whenever I'm going to draw a graph coloring is done, so the graph should be in a plane without the edge crossing, then only the coloring should be done. So a graph is a planar if it is going to be drawn in the plane without the crossing edges. So according to four colors theorem, so for every planar graph, what I'm going to consider, so the chromatic number should be less than or equal to 4. So whatever the graph we are going to take, that should be a planar one. So then the chromatic number should be less than 4 only. So whatever the graph it is, it may be a small, it may be a big. No, whatever the graph it is, so the chromatic number of the graph should be 4. So without the edge crossing needs to be done. So consider this graph. So in this graph, so what I'm going to do is, so I'm going to draw a vertex here. So in this vertex, so I'm going to take the first curve, find it out whether it should be less than or equal to 4 or greater than or equal to 4. So then I'm going to draw green, so red and then green in this case, and this should be yellow, and then this one I'm going to draw as green again or red again, and this should be green, then I'm going to take this as yellow here, and this one I'm going to consider as blue in this case now, and I'm going this should be red, and this should be green, and this should be blue, and this should be red. So how many colors I'm going to consider in this bigger graph is that one, so yellow, two red, green, and then four. So the chromatic number is 4. So less than or equal to 4. So that is the theorem what I'm going to suggest here. So according to color theorem, for every planar graph, the chromatic number should be less than or equal to 4. So what is graph coloring? So graph coloring is nothing but assignment of colors to the vertices of the graph, and strictly speaking that the coloring is nothing but the proper coloring if no two vertices is going to have the same color. And then NP complete, so NP complete is nothing but click problem. So it is one of the problem. So how many colors are going to be there in that key maps? That is one of the example of that. So graph coloring is entirely different. So assignment of color that should be done in distinct way such that no two vertices are going to be have the same color. That should be the collective problem. So assignment of labels or coloring the edges or vertices of the graph is nothing but the graph coloring. Okay, so the assignment of labels and then colors to the edges and vertices of the graph is nothing but the graph coloring. The most common type of graph coloring are the edge coloring and then vertex coloring. The most common type of graph coloring are the edge coloring and then vertex coloring. Okay, so the most common type of graph coloring are the edge coloring and then vertex coloring here. So what is this edge coloring here? So the assignment of labels or colors to each edge of the graph such that the adjacent edges must have different colors. That is the edge coloring. Vertex coloring means so the assignment of labels and colors each vertex of the graph such that no edge is going to be connected identically with the colored vertices. So the graph coloring will be of two types. So edge coloring. So edge coloring and graph color vertex coloring are almost all same. That the no two edges are going to be coincide with each other, and similarly the vertex means no two adjacent vertices is going to should have the same color. So that is the problem of edge coloring and then vertex coloring. So the assignment of labels or colors to each edge of the graph such that the adjacent edges must receive the different colors. An assignment of labels, each vertex of the graph should be identical to each other. So let us consider the first one that should be. So let us consider the first one that should be edge coloring. So the graph is going to have the edges. So this line, what I'm going to do is green color. So then it should be red. If I'm going to draw on a green here also, then it should be also this matches the same color. That's why it is not possible. And then blue. So the blue is also going to be different thing. So green, red, and then blue. Again, if I'm going to draw the green color. So the edge coloring problem can be formatted as vertex coloring problem. Okay. So let us consider an auxiliary graph and be the graph. I'm going to color it. L of G contains the vertex for every edge in the graph, and there is an edge in the L of G drawn between the two vertices if their associated edges in the G should share the common vertex. So L of G contains a vertex for every edge in the graph, and that should be drawn between the two vertices, and there should be associated edges that is going to be there. So example, auxiliary graph. So what should be the auxiliary graph? So the two graphs are almost similar in nature, then I can able to say that should be the auxiliary graph. The coloring of the graph should be of two types, what I said, that should be vertex coloring and the edge coloring. So the vertex coloring means that so the vertices of the edges are going to be coincide with each other, should not coincide with each other, and edge coloring means the adjacent vertices are adjacent edges are not going to be coincide with each other. So if I'm going to apply both of this into one single graph, then the graph look like this. So they should be the vertex and edge coloring graph. So one of the reason that the graph coloring should become the subfield of graph theory. So that means that it should be the branch of mathematics, which should be also known as four coloring problem. So the graph coloring So you should be of two types, like vertex coloring and edge coloring. Vertex coloring and edge coloring is going to be combined. Then I can able to grab what I'm going to call as vertex and edge coloring. So what is this edge coloring here? So for every edge color problem could be transformed into a vertex coloring problem, and the coloring of the edges of the graph should be same as the coloring the vertices, such that not every vertex color problem can be transformed into edge coloring problem. Every vertex problem can be transformed as an edge coloring problem. So that every graph has a line graph, but not every graph in the line graph is of the same other graph. So every graph has a line graph, but not every graph in a line graph of the other graph. So the edge coloring should be same it as vertex coloring. Not every vertex color graph should be transformed into edge coloring. Edge coloring here. So given a graph, edge, when I'm going to color the edges such that the edges are going to be shade the vertex, do not shade the color as well. So if I'm going to have a graph like this, so when I'm going to make it as one color, and definitely they should be another color, right? And similarly I can able to do another color so that no two colors are going to be coincide, and this should be the another color. So if I'm going to draw another thing, so definitely I have to give the another color. And here, so to give that it is not possible, and if I give this one also not possible. So definitely I have to give compulsory another color here. So that means the number of colors should be 4 in this case. Edge coloring, so that means it should be similar to the vertex coloring, so except the edges are going to be colored, and adjacent edges is going to have the different colors. So if I'm going to draw the graph, and then each graph is going to take different types of edges also, and if I'm going to color it, so the graph should be look like this, colorful with the different colors of the edges. And vertex coloring, so the vertex coloring is nothing but assignment of labels and colors such that no two vertex are going to be coincide with each other at the same time. The chromatic number of the graph should be less than or equal to 4. So if you look at this, if I get a hexagon, so the number of colors that are needed in this hexagon is 1, 2, 3, and then 4 in this case. And here it should be 2 only, and here it should be 3, red, green, and then blue, and here also it should be 3. So all the time the chromatic number of the vertex, so that means the number of colors that are needed to color it, that should be less than or equal to 4 only. So according to the 4 coloring theorem. So look at this. So this is the graph. Suppose we are going to have our map. So I have to mark those states which should be of different colors such that no two colors are going to be coincide with each other. So in this case, so this is the one region which is not coincide with the other region, and here also not region. It should be also not coincide with the other region, not the. So if I'm going to take a proper 6 coloring and 4 coloring, So how the graph look like this. So if I'm going to consider this graph, so and definitely I need the six coloring. So there should be 1, 2, 3, 4, 5, and then 6. So in this case, the diagram is changed. Then just I need only four colors. That should be red, blue, and then green, and then yellow. So why are going to be prefer this graph coloring here? So here the many of the problems are going to be formatted as a graph coloring. So including this timetabling, scheduling, register allocation, and canvassing. So a lot of research also going to be done in this area about the problem space. So the many problems are going to be formulated as a graph coloring. So including timetabling, scheduling, register allocation, channel assignment, and all. So a lot of research also going to be done in this area in order to cover more problem space. And some of the terminologies what I'm going to remember in graph coloring is the gray coloring. So what is this gray coloring of the graph? So the gray coloring of the graph is nothing but mapping of vertices into integers such that the adjacent vertices is going to have the different integers. So the K coloring partitioning is nothing but so the object should be of distinct subsets such that the vertices from the different subsets is going to have different colors. So the K coloring means that so the coloring of the graph is a mapping of vertices of the graph such that the adjacent vertices is going to have the different integers. So the K coloring partitions is also going to be disjoint subsets such that the vertices from different subsets are going to have different colors. Terminology K colorable. So graph is said to be K colorable. It is going to have the K coloring, and chromatic number means the smallest integer k which is going in which the graph is k colorable is also called as chromatic number of the graph. So k colorable means a graph is said to be k colorable if it is going to have the k coloring, and chromatic number means that so the smallest integer k for which the k colorable is called as a chromatic numbers, and the smallest integer that are going to be need is nothing but the chromatic number. So what is this terminology here? And k chromatic graphs. A graph whose chromatic number is k is called k chromatic graph. So a graph whose chromatic number is k is called k chromatic graph. And coloring of the graph means that it is going to be assigned the color to the vertices such that the adjacent vertices are going to be given different colors. Okay, so the coloring of the graph is going to assign the colors to the vertices such that the adjacent vertices are going to be given by the different colors. So example, so this should be the graph, should be the four chromatic. So let us consider a problem here. A state legislature has a number of committees that meet every week or 1 hour. So how we are going to schedule the committee meetings such that the at least amount of the time is used, but such two committees with overlapping membership does not meet the same time. The state legislature is going to have the number of committees, so that is going to be meet every week for 1 hour. However, going to schedule the committee meetings such that the least amount of time should be uh, used, but no two committees going to have the membership. So this is another example of vertex coloring. The meeting is going to be scheduled as a vertex, and the edge is going to be represent the conflict between the meetings. So the chromatic number of the graph is also 4. So that means the 4 hours suffice to schedule the committee meetings without conflict. So for this problem, I'm going to consider the committee meetings as a one vertex. Communication that should be done or conflict between the two meetings is going to be represented as the edge. So let us consider another example like each cell. Each cell is an vertex and each integer is going to also a color. The vertex is adjacent to another vertex if it is going to have the one of the following. So that should be same row, same column, and same 3 by 3. So the vertex coloring is also going to be solved in the pseudo. Okay. So each cell is a vertex here and each integer label is a color, and the vertex is adjacent to another vertex if it is going to have the following. And next one is Vigen's theorem. So what is this Vigen's theorem? So Vigen's theorem is nothing but the vertex degree. That means the number of edges that are going to be entered in the edge is nothing but Vigen's theorem. So any graph with maximum number of degrees of delta can be colored with at most delta plus 1 colors. So edge coloring is almost all similar to vertex coloring, what I said previously. And the graph which is going to have the same number of vertices and then same edges, then I can able to say that graph as an auxiliary graph. So example of this auxiliary graph will be, so this is one auxiliary graph and this another auxiliary graph. So here, so both are going to have the same number of vertices and same number of edges. So both are same. So we are going to be coloring the edges of the graph such that multiple edges are going to have the different color. Similarly, I'm going to consider another graph. So vertices is going to be done. So that no two vertices are going to be coincide with each other. Okay. So that should be about the auxiliary graph. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.